a few very important properties. Those properties which have practical significance, like a shift in time will not change the frequency content, but only add a delay in it. So this is the property. And then another one is that if you want to shift uh, the uh, the complete signal from one band of frequencies to another, you multiply it with an exponential j omega naught n. That'll have the effect of shifting the whole spectrum to omega naught. And this is an important property because it is used in all communication systems. And time reversal is, if you reverse the signal in time, you are reversing it in frequency. And a very simple example I gave you was an exponential. If you change omega naught to minus omega naught, it will become an exponential minus j omega naught. So omega naught will come at minus omega naught. Then was another important property, and I told you about like few others. They may not have that type of significance, but this property which says convolution in time is multiplication in frequency, and I also ask you to do this assignment to prove that this formula is actually, or this relationship is actually true. And converse is also important, especially in digital communication, which says if you're multiplying two signals, its effect is that it is convolution in frequency. Uh, in especially again digital communication, we multiply a signal, though we are multiplying it the cosine, but still this property holds good. And then is another interesting property which can again be very easily proved, and it is that which is called Parseval's theorem, that the magnitude square, whether you do it in time or you do it in frequency, they are the same. So means if you want to compute the power or the energy in the system, uh, you can just either add them or add absolute, take absolute of all the samples, square them and add them together. Or if you have its Fourier transform, then you can just integrate the magnitude square of the Fourier transform. They both will give you the same value. So, this is what I ask you to do as a homework assignment. It's an important property. Sometimes convolution, like we spend time in learning about convolution. For example, if I ask you to convolve a and uh, u and with b and u and where I tell you a magnitude is less than 1 and b magnitude is less than 1. So you have to do this flip and drag. You need to draw both signals, do the k-axis, then flip one signal and then drag it on the other, do all these summations. So you go through a lot of trouble actually in implementing the convolution. So if this, you make this k-axis, this is ak, and the second signal is like this, and this is also k-axis, this is n minus k, and then you have no overlap region, then a partial overlap, and it will remain a kind of partial overlap because but you have to compute the summations, you are doing multiplication. But if you implement the same in frequency domain, okay, uh, and then you can definitely that you implement it in frequency domain where it says that just take the Fourier transform of one, take the Fourier transform of the other, multiply them together, and then take the inverse Fourier transform. It will also give you a quick answer, and you don't have to get into time, do all these flips and drags and summations. So a n u of n is 1 over 1 minus a exponential minus j omega, and the other one is 1 over 1 minus b exponential minus j omega. Okay, so this is the multiplication, and then you need to split it into partial fractions, and I hope that we know if you consider exponential minus j omega as an x, so you get 1 over 1 minus ax and 1 over 1 minus bx. Okay, and split them into partial fraction by having a coefficient a naught and having a coefficient a naught. Well, I'll not get into partial fraction expansion, but I hope that every one of you knows how to compute the partial fraction expansion. Usually you hide this one. Okay, for finding a naught, you put x is equal to 1 over a and place it here. You get an a naught and place it here, and then you hide this one, this part, and you put x is equal to 1 over b and you put it here and you get the a1. So you get a naught and a1, and then inverse Fourier transform is very simple, which primarily is the same. You have this coefficient a naught, and it is a n u of n plus a1 b n u of n. So you should get an answer like this. So depending upon the value of a naught, and if they also involve an exponential, then you need to do requisite shift to these signals. So this is an important property. Another reason for this to be important is, let's say you have finite dimension signal. So you have the signal 0, 1, 2, let's say it is 1, 2, and 3, and you are asked to convolve it with this signal 2, 3, minus 2. Still it holds good. Still the multiplication thing is hold good. You take Fourier transform of the one, this one. This Fourier transform is 1 plus 2 exponential minus j omega plus 3 exponential minus 2 j omega, and then multiplied with this Fourier transform. This Fourier transform is 2 plus 3 exponential minus j omega minus 2 exponential minus 2 j omega. So for your convenience, you can again write it as a polynomial by replacing exponential minus j omega with an x. So 1 plus 2x plus, this is very interesting. I found it very, very interesting. So this is the first polynomial, and the second polynomial is 2 plus 3x minus 2x square. Interesting because I found it interesting that convolution is actually multiplication of two polynomials, and that is something we have been doing from our high school algebra, that you are asked to multiply two polynomials. So convolution is if you look at this signal and convert it into polynomial. First is this 1 plus 2x square plus 3 plus 2x plus 3x square. Similarly, here is 2 plus 3x minus 2x square. So no matter what is the length of the signal, just do this conversion into a polynomial. It means that as if you have taken the Fourier transform. So Fourier transform of a finite dimensional signal will not add any value otherwise. It's just the same coefficients, but with every coefficient you have an exponential to the power, which is its index. And so you multiply, so 2 ones the 2 plus 2 2's the 4x plus 2 3's the 6x square. So, and then you multiply it with 3x, so it is 3x plus 3 2's the 6x square plus 9x cube. With minus 2x square is minus 2x square minus 4x cube and minus 6x4. This is very interesting. And you add, you get the answer of the convolution. So it is 2 plus 7x. So this is 12 minus 10 plus 10x square and plus 5x cube minus 6x4. And you can just draw this one. First sample is 2, then is 7, then is 10, then is 5, then is minus 6. A sheer uh, polynomial multiplication will relieve you from all the complex tricks you have learned to perform convolution. Those were like flipping the other and then dragging and then or making copies of the impulse response with this magnitude and then adding them together. Uh, so you get an answer. It's kind of the same that you are shifting. Uh, Polynomial multiplication is almost the same, that you are shifting the impulse response and scaling it according to uh, the value of the signal, and then you are adding them together. So it is precisely the same what we did, as with the basic understanding that this is what the convolution does. The linear and time invariance property, that linearity says that you split the signal into samples, and then time invariance says that uh, just make copy of the impulse response and scale it accordingly, and then add all the samples together. So this is very important property, and we must use it. Then there is another important property which says that if you we have already seen that if you flip a signal, you flip its Fourier transform. But what if you take its conjugate? So if you take conjugate, uh, so uh, so if you take conjugate of a signal, you get this, which is called that it exhibits Hermitian symmetry. Okay, the Fourier transform exhibit Hermitian symmetry. There are other properties which says if signal is evenly symmetric, then Fourier transform is also evenly symmetric, which can be easily proved from this property, that if you flip and it is not changing, so you flip the Fourier transform, it will also not change. Similarly, if the signal is odd, its Fourier transform is also going to be odd. And you know what an odd is. If you flip, there is a difference of a sign, so this is an odd signal. If you flip it, it will be the same if you change the sign. Otherwise, it will have the mirror image on the diagonal side. So even is even, but interesting is what if signal is real, that its conjugate is same as, and most of the time we deal with real signals. So if your signal is real, this very interesting expression holds good, which means that this will be equal to, so its Fourier transform will be equal to that you first change exponential j omegas into exponential minus j omegas, and then replace every j with minus j. So this is called Hermitian symmetry. So this property is again very important property from implementation perspective. So as a matter of fact, this property is saying that if signal is real, so there is a relationship between what you see on the positive side and what you see on the negative side of the frequency axis. And so this property, that if signal is real, then x exponential j omega is going to be same as x conjugate exponential minus j omega. Okay, it's an important property. Uh, for example, if you have this signal, let's say, just taking a very simple example. This is 1, this is 2. So its Fourier transform is 1 plus exponential minus j omega. And it says that if it is real, so you take the conjugate of this. So take, obviously a real signal taking conjugate will not change the signal. So but here you do this operation. First you change omega to exponential minus j omega, so you get 1 plus exponential j omega. And now you take its conjugate. So you're going to get again 1 plus exponential minus j omega, which is the same. Okay. So why should I care about this property? Obviously, though there is a mathematical property. So we leave it, though we can prove it mathematically as well. But what value is it adding? The value is once you consider its magnitude and phase. So if it is a real signal, its Fourier transform magnitude is going to be evenly symmetric. This is the consequence of Hermitian symmetry. And its phase is going to be odd symmetry. So phase is going to be odd symmetry and magnitude is going to be evenly symmetric. So for any Fourier transform, and we have actually seen it once we were saying a of n, u of n, we saw its Fourier transform is 1 over 1 minus a exponential minus j omega. This is important that you can only take the Fourier transform if a magnitude is less than 1. So this expression, once we plotted, if you remember, its magnitude was like this and its phase was like this. So magnitude evenly symmetric means I should only compute half of it, and because uh, in digital signal processing you actually have to prove actually have to compute the Fourier transform. So signal is real, you precisely know that just compute the half of the Fourier transform from 0 to pi, for example, and just replicate it on the other side, the same magnitude, and phase the flip the phase and plot it. So you don't have to actually compute it using the formula. So it has a pretty complex formula for computation. So this is an important property that tells us that you don't have to actually calculate the Fourier transform for minus pi to pi, just compute it for 0 to pi. And many books would not even care to plot the Fourier transform minus pi to pi. In books, in publications, they only plot, even if it is for images, as a matter of fact, it is only plotted from 0 to pi, and we know that it's going to be symmetric around this axis. So this is an important property of the Fourier transform, and I'll be showing the MATLAB code as well. ये important थी property. Then, for example, this is an interesting signal A. So this is an interesting signal A magnitude n. So if you plot it, it is this signal. Okay, it is evenly symmetric, and if a signal is evenly symmetric, this yet another property which says if signal is evenly symmetric, so you flip it, you are going to flip the Fourier transform as well, and because it is real, so it also exhibits Hermitian symmetry. So if you combine both of these, so if the signal is real and even, its Fourier transform is also going to be real and even. So if it is real and even, its Fourier transform is also going to be real and even. So it's, or another way of looking at it is that the only way that you can make a Fourier transform real and real, Fourier transform real, is that signal has to be real and even. For example, this is a signal that is real and even. Okay, 0, -1 and 1. So this is a real and even signal. So if you take its Fourier transform, it will be a real signal of omega. There will be no j in it. So j, for example, and we know like this sample and this sample, an exponential with negative omega, this is an exponential positive omega. You can combine them to make them into a cosine. So its Fourier transform is 2 plus exponential minus j omega plus exponential plus j omega. And this is the formula for cosine 2 cosine of omega, which is real. Okay, and real and even actually. Well, if you plot cosine, cosine is it's a raised cosine riding over 2, so it's going to be a real and even function of something like this. So real and even. So important that the only way you are going to get rid of a j on the right hand side is that if your signal is real and even, a real and even signal, like in this example, This is real and even signal. And if you see its Fourier transform, you will not find any j in it. So I'll not get into the derivation, but you can uh, get in get the derivation done. So this, you remove this, it from take 0 minus infinity to 0, and then from 0 to or 1 to positive infinity. So these are the two transformation, and you add them together to get to this answer. Perhaps this you can also do as an assignment for your quizzes and exams. Please do this as an assignment. A of n, U of n, this signal. Preferably break it down into two signals. One is that running on the positive side and from 0 to infinity. The other is which starts at -1 and going towards negative split. So you already know Fourier transform of this, which is a of n, U of n. It is 1 over 1 minus a exponential minus omega. And the other one has a shift by 1. So use the property. Instead of using the summation, use the property and compute the Fourier transform. So this is again yet another case that it is real and even. If it is real and even, you are not going to see any j, means there's going to be no phase in the Fourier transform, because phase only comes in if there is a j. Then you do tangent inverse imaginary over real. But if imaginary is not there, it is 0. So tangent inverse 0 is 0. So there is no phase. But you can see that this sample will pair with this sample will pair with this sample. A 0 sample seem not to be paired. So one cosine this and one will convert into cosine like this. So just looking at this, I know it's Fourier transform. Okay, and converse is also true. Converse means that if you see a cosine, you know they are going to be two in the frequency domain as well. But here you see that this is the Fourier transform you write, and then you pair them together and convert them into cosines with two magnitude, two cosine of this frequency and two cosine of this frequency, and then a DC value like this. So this is again an important property, that if you are given a signal which is real and even like this. Okay, so just by looking at it, I know there are going to be two cosines. These two are going to make one cosine and the other two are going to make another cosine. So it is going to be 2 minus 3 into 2, 6 cosine of omega plus 2 into 1 is 2 cosine of 2 omega. So I can directly write the answer, that this is the answer, is a real and even function in the frequency domain as well. And if you plot these from -pi to pi, okay, you will see whatever you are going to see on one side, you are going to see the same thing on the other side. So if it is real and even, very important property, real and even means zero phase, there is no phase in it, and you are going to see symmetric Fourier transform. Okay, so we'll get back to this. We'll keep getting back to this particular aspect, that these are also called zero phase system. If an impulse response is real and even, then the Fourier transform has zero phase. What is the consequence of the linear phase? So we'll come to it. But another important aspect is, let's say if the same thing. So I know that this is a Fourier transform. But what if I shift it, give it a shift in time? So the same signal, shift in time. Okay, so it is this. It was 1, then it was -3, then it was 2, then it was -3, then it was 1. And if I shift it by a factor of 4, So now it is at 4. Sorry, this is at 4, this is at 3, this is at 2, this is at 5, this is at 6. So what I've done, that this signal shifted by 4. So 0 now is at 4. So I only use the shift property, which says shift in time is. So what is the property? Let me see. जी आपको याद है shift in time is x. जी जी बताएं.
So exponential multiply होता है.
Yes, so shift in time is multiplication by an exponential. अच्छा बड़े ना core concept हैं signal processing के, okay, especially these, and they have implications in the rest of the course. इसलिए हमने थोड़ा सा इस पे time slow ली, but we have spent a lot of time because this is the core basic concept which will feed into all the topics that we shall be studying. तो इस वजह से हमने इस पे थोड़ा सा ज़्यादा टाइम लगाया. ठीक है, अब ये है कि आपने शिफ्ट कर दिया तो जैसा आपने कहा जी ये तो एक्सपोनेंशियल से मल्टीप्लाई हो जाएगा. यू आर एब्सोल्युटली राइट. एक्सपोनेंशियल माइनस J4 ओमेगा अंदर वही आएगा. पहले कोई फेज नहीं था. अभी वंस यू शिफ्ट, दिस इज अ लीनियर फेज, राइट. दिस इज अ लीनियर फेज बिकॉज आपको पता है कि कोई कॉम्प्लेक्स नंबर होता है जब 2 + 3J, तो उसका आपने लिख सकते हैं मैग्नीट्यूड की फॉर्म में 4 + 9 एक्सपोनेंशियल माइनस J tangent inverse imaginary over here. So this is how you can write a complex number as a complex number or in a polar form where it has a magnitude and a phase. The same thing can be done with a function as well. If you have a function and you are asked to write it in polar form. So this function written in polar form will only have a magnitude and an exponential J0 because there is no term. So there is a magnitude, and so for example, if I write 2 as a polar form, so you say 2 as a polar form, 2 has only real, so you can write 2 as a 2 exponential J0. It has 0 phase because there is no negative part. So if you draw this on a complex axis, it is only going to be on the real axis. There is nothing on J. So, but the interesting is like if you shift it, you only add a linear phase in it. Okay. So the phase of exponential minus J4 is a linear phase, exponential minus J4 omega, and inside is the same thing, so sine of omega plus 2 cosine of 2 omega. Okay. So if I write the magnitude and the phase, so you say this is the magnitude, and you say phase is J compares with J exponential with exponential, so minus 4 omega is the phase. If you plot this phase, it's at 1, it is minus 4, so this is the phase. Okay, at 1, it is minus 4, so it's a linear phase. It's a linear phase, okay. So again, very important aspect in signal processing, which says if you shift a signal, the amount of shift, if it is by 2 and signal is real and even, means for every sample there is another sample. Every sample is another sample on the other side of the symmetry, axis of symmetry. So you have all real and a linear phase, exponential minus J 2J omega. So its phase is minus 2 omega. So you can plot the phase, it is minus 2 omega. This is like this. Okay. At 1, it is going to be minus 2. Pass it through the 0. So it's a linear phase system. Now, this phase is just a straight line, a linear phase system. So it will show you the matter. So this is an important. So what we have seen, all the useful pairs, delta n में all exponentials 1 होता है. A constant has a DC value. So this ugly looking summation is only to show you that it's symmetric at every 2 pi. So but 1 has only a DC value. So we have gone through this 0 to magnitude is 2 pi. So this is its Fourier transform. and then a copy at 2 pi minus 2 pi, 4 pi minus 4 pi. Similarly, in exponential of j omega, you have a sink at, oh, an impulse at omega naught. This is the Fourier transform. But then you're going to see it every 2 pi, 2 pi, 2 pi, 2 pi. And cosine, you're going to see two of these. One at omega naught, the other one is at minus omega naught. And obviously it is pi, so scale by. So similarly, what happens if you have A of n, U of n? You don't see that ugly looking summation. The reason you don't see that ugly looking summation is because the expression itself is symmetric. If you put omega is equal to omega plus 2 pi, you are again going to see the same thing. And if you draw this, you again keep seeing the same, keep seeing the same, keep seeing the same at every 2 pi. So if its Fourier transform looks like this, you are going to see this. Every 2 pi, it will replicate itself. Because this is inherent in the formula, that the formula itself is periodic over 2 pi, and I've told you that because of this reason, we only plot the Fourier transform from minus pi to pi. And I further told you that if it is real, then you, even looking at it from 0 to pi suffice, because you know the same thing you're going to see on the other side. And if you're plotting the magnitude and the phase, then magnitude you're going to see like this, and the phase is going to be odd symmetric. So ये important चीजें हैं we must know. So this almost brings us to the last few topics, and this is, you know, how we started. If you have an impulse in an LTI system, the output you get is called an impulse response, and if input is exponential j omega, you get exponential j omega out. So exponential j omega n is an eigenfunction to an LTI system, and comes with another expression which tells you that how it is going to shape your exponential, how much magnitude of the exponential will be changed and how much its phase will be changed. And that's why H is called as frequency response of the system. And then very important property that we learn, and I ask you to prove it yourself, is convolution in time, but I gave you an idea that how it is proved. It is multiplication. अब देखें यहाँ से for an LTI system, again, this expression is again the most important expression, no matter whether you are learning signal processing or image processing or deep learning or pattern recognition or digital communication. This expression is a very important expression, which says convolution in time is multiplication in frequency domain. Why it is important? Let me tell you that. Okay. So convolution in time is multiplication. Because the whole purpose of signal processing is to process a signal. Okay, this is what signal processing is. You are going to process a signal. So in this course, and about 95% of the signal processing, not 100%, you process a signal through an LTI system, okay, a linear time invariant system. You basically, and if you process, so you go to focus, and I showed you in deep learning as well that this is where the magic is. The magic is in h of n, that h of n is going to define that what it is going to do with your x of n. Okay, and it is in time domain, it is very difficult to figure out what is going to happen to my signal. Okay, and but inverse problem is even more interesting, that okay, this is my signal and this is what I want to do with it. Okay, it's more interesting, and I'll shortly you will figure out why I'm saying this. So whole purpose of signal processing is to process a signal. Process a signal means to perform convolution. Mostly perform convolution means A system is nothing but an impulse response. So you got to find what the impulse response is doing to your signal. But in frequency domain, it's interesting. It is telling me that actually, whatever signal I have, so I have a Fourier transform of a signal, let's say, and I find out that this is the frequencies of my interest, but along comes along are the frequencies which are undesirable frequencies, especially in radio receiver, the radio you listen to. uh, you have adjacent channels. You are playing even in satellite communication, in your cable, and mostly in satellite in communication systems. The slots and even the calls you are making on a mobile, it is tightly packed. The frequencies are not wasted. So frequencies are tightly packed. This is your call. This is your neighbor call. Neighbor call means the guy who got a slot which is adjacent to your slot. And I remember a time where when you used to tune in into the other calls and listen to what is happening in the network by just mobile tuning and seeing that what is happening on the other slots, you can actually listen to the conversation. But if you tune it like this, that you are getting, and sometimes our AM radios, you start listening to channels. So half of your slot and half of the other person's slots, you can listen actually both. In our TV, satellite TVs, you see that sometimes you're watching a channel and two channels are coming, okay, because they're not tuned properly. So means that it is basically has picked half of the frequencies. We're just going to pick this band, half of the frequency, the previous half from this. So this tells me a very interesting thing that if I take the signal in frequency domain, so my edge acts as a cutter, that how I want to shape the frequency or the spectrum of my input signal. I say, oh, I don't want this. So my edge should look like this, and whatever I don't want to see should be 0, whatever I want to see should be 1. So if I pass this to a system which has this type of, so it will remove. And that is why the digital systems are so precise. Either you receive or you don't receive, but usually it will not happen that you're receiving half of one channel and half of the other channel. Usually it will not happen. So this is this relationship is very important, which is telling you, hey, you can just think of it as a cutter, and then you are just shaping the frequency response of your signal. So very important property, which is the this property, the very important property. See, uh, so I'll be showing you a MATLAB code for this. Let me see what all I have to do to show you that. uh, First I need to share with you the MATLAB screen. It's MATLAB. Here's the MATLAB. ठीक है, ये कोड है उसका, ठीक है. So what I'm doing is I'm just generating a random signal, just random. What is random? Random is noise. Random is which has almost all the frequencies randomly spread. So white noise means it has like almost all the frequencies, a little bit different magnitude. So I generate white noise and I compute. So can you see the plot?
Not yet, sir.
Not yet. प्लॉट आपको नजर ही नहीं आ रहा होगा. खैर,
नो सर. सर अगर आप आई थिंक स्क्रीन शेयर कर लेना तो दैट विल बी इजी. अदरवाइज जो है ना वो हर दफ़ा आपकी सिर्फ स्पेसिफिक इस विंडो को शेयर करता रहेगा.
अच्छा, ठीक है, ठीक है, ठीक है, ठीक है. स्क्रीन शेयर कैसे करूंगा मैं? डेस्कटॉप शेयर करूँ? That's what you're saying? आ रहा है नजर?
जी सर.
Okay. So this is noise. Okay, and this is the Fourier transform my filter. And now I have already told you that this is multiplied by this. So what do you expect to see? आपको क्या नजर आएगा जब इसको आप Fourier domain में देखेंगे? If you multiply these two signal, what will you see?
सर -20 से लेकर 20 तक जो पार्ट है वो वाला।
Yes, वो रह जाएगा, बाकी तकरीबन जीरो हो जाएंगे. This is also called colored noise. It's called white noise. The first plot number one is called the white noise because it has noise of all the frequencies, and the second one is called colored noise because you have filtered out some of the noise. So dealing with noise, एक और चीज मैं आपको बताऊं, whether it is your life or signal processing, all the time you are dealing with noise. Okay, those who can deal it in signal processing, so you are successful. Like you can deal with noise, mean you can make communication systems um, and other things. But if noise takes you over, then uh, there's nothing you can do about it because noise enters into the same frequencies जो कि आपके सिग्नल की भी फ्रीक्वेंसीज होती हैं. ठीक है, सो मोस्टली यू कैन नॉट गेट रिड ऑफ दिस नॉइज इफ इट इज पार्ट ऑफ द बैंड वेयर योर सिग्नल इज. ठीक है, उसको बहुत मुश्किल होता है उससे काउंटर करना. बट सो दिस इज इम्पॉर्टेंट. So this property is very very important property which says that if you have, so you can see it here as well, that whatever part you don't want, you make it go to zero, so this goes away. So usually an LTI system, and this is the reason an LTI system is also called a frequency selective system. The LTI system is a frequency selective system that it basically helps you to select a band of frequencies, whatever frequency you intend to select. अच्छा, मेरे ख्याल है यही डॉक्टर अली ने आपको शायद लैब वगैरह दी हो या डेमो करके दिखाया हो, जो इक्वलाइजर्स होते हैं, डिजिटल इक्वलाइजर्स, एंड इन म्यूजिक स्पेशली देयर इज दिस कॉन्सेप्ट ऑफ एन इक्वलाइजर. आपने अपनी गाड़ियों में जो पुरानी गाड़ियाँ होती थी उनमें देखा होगा कि वो इस तरह करके बार्स लगी होती थी. So you can actually change the value of these bars, और यहाँ पे frequencies लिखी होती थी कि which frequencies are you changing. So you can, by using the equalizer, you can emphasize some of the frequencies and some of the frequencies you can de-emphasize. And how we actually implement an equalizer, which just by learning very little signal processing, you can develop your own digital equalizers. How that you have, let's say, a song you are playing, it has different frequency contents. Usually a CD quality music is sampled at around 40 something, 44 42 kilohertz. So from 0 to 21 kilohertz are the frequencies, and you can see that what are the, depending upon the type of music and instruments being played, if you look at the frequency response, you will know that what are the from what is the band look like, what are the different frequencies which are being played in this song. And then you pass it through a series of band pass filter. Okay, a series of filter, this filter, this filter, this filter, this filter, this filter, this filter. So kind of you're shaping, getting different frequency contents of the signal out, and then every signal you can multiply it. So these are these bands of signals, and you are changing their amplitude, and then you are adding them together and you play. So a typical equalizer will look like this, that you have a band pass, let's say a low pass filter, then you pass it through, and remember it's symmetric, so it should appear like this. Then there is another filter. You're not going to leave any frequency, otherwise it will distort your. So you have multiple, depending upon how the number of channels that you split your sound. So you have this, you multiply it with one coefficient, you have this, you multiply it with another coefficient, you have this, you multiply it with another coefficient. So this is usually a good lab for students to perform, and they may just listen to only one part, make the other zero to see a typical frequency. So you may hear if a guitar is being played or a drum is being played and with a certain frequency, so you can listen to only that and rest will go away. Rest of the but if an instrument has contribution in the rest of the frequency band, so you also hear that, but you then multiply, this is A coefficient, B coefficient, 2, 3, 4, and then you add them together. And then you play. So this is an equalizer, okay? And this is the fact that signal processing especially is frequency selective, like cutting the band, putting them into pieces, amplifying one over the other, adding them together, and then play the game. If you have not already done this lab, and I'll very strongly suggest Dr. Ali to design such a lab for you and just have fun with signal processing. And you can do the same with images as well. Okay, you can emphasize more some of the frequencies in your image and see the effect. Okay. Now, if you also extend the same idea of the Fourier transform to an LTI system, which is represented with a difference equation, not the convolution summation, a difference equation, and we know that the constant remains constant. A shift gets onto as an exponential minus j omega. A shift gets as an exponential minus omega. A shift, as you said, shift is an exponential minus j omega. And then this is independent of k, you take it out. This expression, this is independent of k, you take it out, rest of the expression is here. And then you take x on this side and this on the other side, so this is what you get. This is again a very, very important expression in signal processing, that a difference equation, given a difference equation, you can find out its frequency response. Okay. Just solve an example for you to understand it better. So for example, it is y of n minus 2 y of n minus 1 plus y of n minus 2 is equal to x of n minus 6 x of n minus 1. So I am very interested in finding out h exponential j omega. Why? Because that will tell you how the system is going to cut, so to say, the frequency contents in my signal, because even for this relationship holds good. So finding an edge is so important. Plotting its magnitude and the phase is so important in signal processing, that you always want to see that what this system is going to do to your signal. In an LTI system, the only thing it can do is it can select some of the frequency, emphasize some and de-emphasize the other. That's the whole purpose of signal processing, which is using a linear and time invariant system. Okay, so what we do is we take its Fourier transform of both sides. Y is capital Y exponential j omega, minus 2 is constant. This will come as the exponential minus j omega because the shift in time, y as is. It's not going to change the shift, it's not going to change y, the frequency. It will only going to introduce a phase term. Y shift will be a shift x omega minus 6. Yeah. So you take y common and x common from both sides. So y exponential j omega. Common, you have 1 minus 2 exponential minus j omega is equal to, take x exponential j omega common, we are going to get 1 minus x exponential minus j omega. Okay, and then y over x. You bring the x on the other side and take the other part on the other side. You have 1 minus 6 exponential minus j omega divided by is equal to h. Why it is h? Because we know y is equal to h into x. Okay, this is very important. Why it is important? Because it tells me that just by looking at the difference equation, I can find out. I don't have to go through all this painful process of doing all of this. By just looking at the coefficient, I know that these are the denominator and this is the numerator, 1 minus 6x and minus 1. So looking at it, I know the Fourier transform is going to have 1 minus 6 exponential minus j omega in the numerator, looking at 1 and this 6. Looking at the denominator, I know 1 and 2 and 1. So it is going to have 1 minus 2 exponential minus j omega plus 1 exponential minus 2 j omega. So this is going to be the frequency response. So this is, it tells you the same thing, that looking at this difference equation, you can just write down it's h exponential j omega, and if this is given, you can go back and get to the difference equation. And if you take this inverse Fourier transform, you can get an h of n as well. So very interesting again. For example, if I say this is the equation, y of n minus 0.5, and these are the typical question in the exam as well. ठीक है जी, आपसे एग्जाम में इसी तरह के क्वेश्चंस किए जाएंगे कि knowing one thing, you must know all the other things. For example, given a difference equation, you should be able to calculate exponential j omega, h exponential j omega, and also h of n. Okay. So given any one of these, so you must feel very comfortable. Given any one of these, you may be asked to tell us about the other two. For example, we may give you h of n and ask you to find this and this. We may give you this and tell you find this and this. And especially in this equation, we are giving you the difference equation and we are asking you to find out h and h of n. So you must practice that. If you're given one, you can find rest of the two things. So let's find out h. So h तो मैंने भी आपको बता दिया, h exponential j omega is coefficients which are only 1, so it is 1 आ गया. And on the coefficients of y, 1 minus. So coefficient of y, considering they are on the left hand side, coefficient of x will be on the right hand side. क्या आ गया? मुझे पता है कि this is if I take its inverse Fourier transform, I will get h of n, and it is going to be 0.5 and u of n. So you see all the three things in one is the difference equation, the other one is h of n, the other one is h exponential u. So if I ask you to if I ask you 0.3 and u of n, so give the difference equation. Don't get confused. Oh, so I should first find, I say this is h of n and ask you to give you the difference equation. So you have to go through this step. First is Fourier transform 1 over 1 minus 0.3 exponential minus j omega, and I know these are the coefficients of y, this is coefficient of x, so it is y of n minus 0.3 y of n minus 1 equal to x of n. So I can make it a little intricate problem. For example, I say give me 0.5 n u of n minus 2. So give me the difference equation for this. So here you have to use the shift property, but you have to make, the example we did. End of the day, you have an h, and if you have an h, so you have a difference equation. So you must feel very, very comfortable in dealing with all of this. So this brings us to kind of almost the end, but just let me know that this is an important function which is called freq z, and freq z will, if you give an h, okay, so it will, or the difference equation, it will plot its frequency response. So this is the formula. Very important MATLAB function, freq z, b comma a comma n will give you an h, which is the magnitude of the frequency response, and w, which is the phase. So you can plot the magnitude and the phase as is done here. So freq z is an important function in signal processing. We are just, this is almost the end, but yet another example. If you, as I mentioned, if you want to use, let's say, MATLAB, and I ask you to plot the magnitude of the frequency response, how will you do that? So first of all, you can always write this expression, y on the other side. So it becomes minus, it becomes plus, it becomes equal. So this is y on the one side and x on the other side, and coefficient of x are 1, so this is 1, 1, so this is 1. Coefficient of y on the other side, this is 1, this is minus 1, and this is plus 0.1. Yeah. So MATLAB requires you to have b, comma a, comma x. This is what the filter function is. This filter function is, or freq z function is also, the freq z function also requires you to do this. So b comma a comma x. So b is this vector, which is 1 and 1. You see here. And a is the vector in the denominator, which is 1 minus 1 and 0.9 x. So you write freq z, it will plot the freq z for you. So important functions are frequency g, b comma a comma x, and to pass a signal to a difference equation, you have, this is a filter b comma a comma x. So coefficients, writing coefficients of b, coefficient of x, and coefficient of a, which are coefficient of y, is important. And this brings us to the end of the chapter, except which, though I have already told you that this is a low pass filter, because h is as if you have a scissor and you are shaping the frequency spectrum. This is a band pass filter. This is a high pass filter. The maximum frequency is pi. This is a high pass filter. This is a band stop filter, that you are going to stop this band, making the entire band equal to 0. So signal processing boils down to just selecting some of the frequencies from your signal, and that is done by shaping the frequency response in that way. And a crudest way of designing a system is that you have this, and then you take its inverse, Fourier transform, to get an h of n, then h of n, or converting it into a difference equation. Okay, so these are the, so let's no, I think there is yet another topic that is important. Just then we'll take a break. Or let's take a break and then we start this. Let's take a 5 minutes break, please.